PU2 champions, welcome to Dhurandhar series, and in today's class we are going to solve the most important questions from the chapter D and F block elements. So the questions that have been taken here are sourced from PYQs and the question bank released for 25-26 by the PU2 board. Okay, so after watching this one video, all your concepts, all your questions practice will be done, so you don't have to refer any other source. Okay, so now let's get started and understand the weightage of this chapter. So D and F block elements have a weightage of 10 marks. Okay, and how is this 10 marks distributed? So we have here, just a minute, yes, 1 marker you will get 2 questions, 2 marker you will get 1 question, and 3 marker you will get 2 questions. So here I will get 6, here 2 and 2. So total will be 10 marks. Okay. So now first we will solve the PYQs of 2025 to 2022 and then we will go for solving the model question paper. Okay. So let's see the first previous year question of 2025, that is this recent year paper. So the question is match the following with list 1 and list 2. So here you have some catalyst and their I can say the uses of that. Okay, so if you see V2O5, okay, it is used in the manufacture of sulfuric acid. So one has to be C. So I can eliminate these two options. Next we have TiCl4. This is, we know, catalyst that is used very common for the manufacture of polyethylene. So 2 has to be D. So I can eliminate this option also. Correct answer is option number A here. PDCl2 is used for oxidation of ethyne to ethanol, and then you have nickel complexes are used in the polymerization of alkynes. Now moving to the next one. Okay, so students, before moving ahead, so let me just tell you that I can understand at this point of time where we have just 30 days left for KCET and hardly 85 days for KCET 2026, managing these two exams, preparing, having time management is a very difficult and tough task. And at this point of time, something that is very important is a right strategy and a right guidance. So to help you with your preparation, I have started this one-to-one mentorship session. Okay, so this mentorship session is for KCET and PUC preparing students. So here we will have personalized study plan. You can share all your problems, we can discuss subject wise strategies, and I can clear all your doubts regarding your preparation, including your chemistry academic doubts. Okay, so my dear children, if you are stuck in your preparation, if you need someone who can pull you out from this and can actually give you clarity about your preparation, then trust me, I can definitely help you, because I have been mentoring KCET students from last 3-4 years and have guided many of them to top ranks. So the link is there in the description section. Please go there and register yourself for this one-to-one mentorship session. Now let's move to the next question, that is write 2 properties of interstitial compounds. Okay, so this is a 2-marker question. Okay, but the same question can also be asked for 3-marker, where they will ask you 3 properties. Okay, so this is very common and a repeated question. So I'll give you some of the properties of interstitial compounds, like they have high melting point, they are very hard, retain metallic conductivity, and they are chemically inert. So prepare these 4 points so you can write it for both 2 and 3-marker question. Now we'll talk about question number 27. This is also super important. The preparation of potassium dichromate from chromite ore. This reaction has been asked again and again over the years. So please check this answer. First of all, what we do, we take iron chromite, okay, that is FeCr2O4 with Na2CO3 and O2, it is converted to sodium chromite. Okay, then sodium chromite in acidic medium is converted to sodium dichromate. Then sodium dichromate with potassium chloride gets converted to potassium dichromate. Here you just need to remember the reactions. These steps, all if you don't write also doesn't matter, but you should know the equations, and please remember you need to know balanced equation. So prepare these 3 steps of this reaction at least 5 to 6 times. Remember it. This is a must question. Okay. Moving to the next question, 29. What is lanthanoid contraction? And write 1 comparison and 1 difference between lanthanoids and actinoids with respect to oxidation states shown by them. Okay, lanthanoid contraction is also a very important and repeated questions. So let's see first of all what is lanthanoid contraction. It is the gradual decrease in the atomic and ionic radii of the lanthanides from lanthanum to lutetium, okay, with the increase in atomic number. This occurs due to the poor shielding of 4 f electrons, which results in the increased nuclear charge or nuclear attraction on the outer electrons. Okay, so the size decreases very steadily, and that is due to the poor shielding effect of 4f orbitals. This is called as lanthanoid contraction. Now talking about their difference and similarity on the basis of oxidation state. So first let's talk about similarity. So both of them shows a +3 oxidation state, common oxidation state. And if you talk about difference, lanthanides mainly show +3 oxidation state, whereas occasionally +2 and +4, whereas actinoids can show variable oxidation state like +3, +4, +5, +6, as well as +7 also, due to the participation of 5f, 6d and 7s electrons. They both have like 5s, 6d and 7s have comparable energies, so that is why they can show more number of oxidation states. Now moving to the next one, we'll go to 2024 PYQs of March. Which of the following metal oxides are amphoteric? Amphoteric means they can react with both acid and base, so that is Cr2O3 and V2O5. Okay, this is important example. Next question number, answer any three of the following. Each question carries 3 marks. Write the balanced equation for the preparation of potassium dichromate from chromite ore. Already I have discussed. You can see only reactions also, if you write that is correct, but it should be balanced reaction. Next question number 28, the spin only magnetic moment of scandium 3 plus is 0. So see, this magnetic moment depends on what? N is what? Number of unpaired electrons, right? And if you see here, scandium has no unpaired electron, so that is why the spin only magnetic moment of this one is 0. Next, alloys are readily formed by transition metals. So because of similar radii and other characteristics of transition metals, alloys are readily formed by these metals. You can see bronze, brass, they all contain transition elements. Next, write the structure of the manganate ion or MnO4 2 minus. So you can see this is the structure MnO4 2 minus. It is green in color and the tetrahedral shape is there. Okay. Next, what is lanthanoid contraction and mention two consequences of it. So we have already discussed what is lanthanoid contraction. Consequences we will be discussing in the next question. Okay. Now we'll come to 2023 March paper. So which of the following elements is not regarded as a transition element? So if you know, for transition element, the condition is you need to have partially filled d orbitals, right? You need to have partially filled d orbital, either in the ground state, or in the common oxidation state, right? So now if you see, manganese has an electronic configuration of 3d5, which is it is having unpaired electrons. Scandium, if you see, it is 3d1, and if you see zinc, it is 3d10. Okay, in both common oxidation state and in the ground state. So it has no unpaired electrons, so this is not a transition element. In fact, this is regarded as pseudo transition element. Okay, pseudo transition element. Now moving to the next one is actinoids exhibit a greater range of oxidation states. So we have just seen in the difference between lanthanoids and actinoids. Lanthanoids has mainly +3, sometimes +2 and +4 also, but actinoids show +3, +5, +6, +7. So what is the reason for that? Next question is zirconium and hafnium have almost the similar atomic radii. So this is very simple. First of all, due to the comparable energies between 5f, 6d and 7s levels, the electrons can easily be donated for bonding, and that is why they show variable oxidation states. Next, zirconium and hafnium have identical radii, that is because of lanthanoid contraction. Now coming to 3a, the transition metals and their compounds are known for their catalytic activity. Give two reasons. What is Mischmetal? Okay, so this catalytic activity is also very important question. Okay, lot of time it has been asked. You need to write at least 3-4 properties why the transition elements behave as catalyst. Okay, so the first one is they have variable oxidation states, large surface area and presence of partially filled d orbitals. Next, what is Mischmetal? Mischmetal is an alloy of lanthanoid, 95%, iron 5%, and some traces of sulfur, carbon, calcium, and aluminium. Now let's talk about 2023 March paper. Okay, we're continuing with that. Explain the preparation of potassium permanganate from MnO2 with the equations. Okay, so this question is also very important. Both the preparations of potassium dichromate and potassium manganate you should prepare. So if you see MnO2, how it is prepared, first of all, MnO2 is treated with KOH to give you K2MnO4. Then this K2MnO4 is like MnO4 2 minus, okay, that is your manganate. In the acidic medium gets converted to permanganate. Even if you don't write these statements, that is fine, but the equation should be written in the balanced form. Now moving to the next one, 2023 May paper, the valence shell electronic configuration of Z equal to 24. So this is chromium, right? And its configuration is 3d5 4s1. So that is your option number B. Next, write 2 consequences of Lanthanoid contraction. So in the previous question, I told you that in the upcoming slides we will discuss. So here I have given you almost 5 consequences. You can remember any 3 at least, so that if 2 marker, 3 marker, any section it comes, you can write down. So first of all, due to Lanthanoid contraction, the atomic radii of zirconium and hafnium is almost same, and it is difficult to separate them. That's the first consequence. Second is the covalent character of the cation increases. Okay, now what happens because of the charge density, because of the smaller size, the covalent character, the tendency to polarize the anion increases, so the covalent character increases. Electronegativity of the trivalent ions increases slightly. This is important. Next one you can write. Second point, basicity decreases from lanthanum to lutetium. Okay, as the size increases, the bonding increases, and the basicity, release of OH minus becomes difficult, and basicity decreases. Next, standard electrode potential values increase. Now, as the size decrease steadily, the tendency to gain electrons will increase, and the reduction potential will increase. Okay. Next, we'll talk about write the balanced chemical equations in the manufacture of potassium dichromate from chromite ore. Okay, so that we have already discussed. You can write down first iron chromite to sodium chromite, then sodium chromite to sodium dichromate, sodium dichromate to potassium dichromate. This reaction, as I told you, with balanced equations, you should remember. Now, next question, transition metals and their compounds act as good catalysts. Give 2 reasons. Already we have discussed this question. Between scandium 3 plus and copper 2 plus, which is colorless. So remember, for color also, we need unpaired electrons. Okay, whichever will have unpaired electrons, that will undergo DD transition, and then there will be color. Now, if you see scandium 3 plus, the number of unpaired electrons is 0, whereas in copper 2 plus, the number of unpaired electrons is 1. So definitely scandium 3 plus will be colorless. So if you see here, transition metals behave as catalysts due to variable oxidation state, large surface area, and presence of incompletely filled d orbitals. Next, between scandium 3 plus and copper 2 plus, scandium 3 plus because of lack of unpaired electrons. Now coming to 2022 March paper, name the transition element present in the bronze alloy. Okay, bronze alloy. Next, calculate the spin magnetic moment for ferric ion. Ferric ion, please remember this one, ferric ion is there. Next, between scandium 3 plus and copper 2 plus, which is colorless. Already we have discussed B part. Let's see the first one. Bronze alloy has copper. Okay. Next, spin only magnetic moment of ferric. Okay, if you see Fe electronic configuration is 3d6 and 4s2. Now Fe3 plus will have what? 3 ferric ions means Fe3 plus. 3 electrons will be lost, so it is 3d5. So if I draw the structure is like this. 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. Okay. So now what will happen? N value is equal to 5 here. Mu is equal to root over of n into n plus 2. That is equal to 5 into 7, which is equal to 35 root over. Okay. And this is equal to 5.9 bm. Bohr magneton. Clear? Okay, next we'll move to question number 3 here. Write the balanced chemical equation for the manufacture of K2Cr2O7 from the chromite ore. Already we have discussed what is lanthanoid contraction and mention any 2 consequences. This also we have discussed. Let's see once again. The gradual decrease in the atomic and ionic radii from lanthanum to lutetium is called as lanthanoid contraction. And what are its consequences? Zr and Hf, zirconium and hafnium will have similar radii, covalent character increases, electronegativity increases, basicity decreases, and standard electrode potential increases. Any 3 points you can remember. Now move to July 22. Zn2 plus salts are colorless. Explain why. Again, here you know that in Zn2 plus the configuration is D10. So there is no unpaired electrons. And if there is no unpaired electron, then there will be no DD transition. Next, sixth one, calculate the spin-only magnetic moment of Cr3 plus ions. Which transition element does not exhibit variable oxidation states? Okay, so fifth one, if you see, because d orbitals are completely filled, there are no unpaired electrons. Next, calculate the spin only magnetic moment of Cr3 plus. So Cr is having the configuration of 3d5 and 4s1, and we have Cr3 plus, that is give me 3d3 configuration. Okay, and now the magnetic moment is root over of 3 into 3 plus 2. 3 plus 2 is 5 into 3, that is root over of 15, and which is almost equal to 3.8 Bohr magneton. Okay. Next, to calculate here which transition element does not show variable oxidation state, it is zinc, and one more element is there, that is scandium. Scandium only shows +3 state, whereas zinc only shows +2 state. Clear? Okay. Next question, write the balanced equation for the preparation of, potassium dichromate from the chromite ore. Already we have discussed this question. Lanthanoid contraction and mention the cause of it. So I'll just mention the cause here. The cause is because of poor shielding effect of 4f orbitals, right? Poor shielding effect of 4f orbitals. Okay. Next is mention the gas liberated when lanthanoids react with acid. See, lanthanoids are also metals. When they react with acid, you will get salt plus hydrogen gas. So that is why H2 gas is the product here. Okay, now we will move to question bank. Okay, so I have taken almost all the questions of the question bank. So please go through this and you will be now not having any confusion that any question is left. But very simple questions are asked, so don't need to worry. You just need to know certain basic things and then this chapter is done. So let's start with, because in D and F block you will get 2 marker and 3 marker questions. So we will discuss 2 and 3 markers separately. Okay, there are almost 40 questions in 2 markers and almost 40 questions in 3 marker also. So let's get started with the 2 marker question first. Write the electronic configuration of chromium and copper. We know that they have slightly different configuration, so that is why this is asked. Next is question number 2, that is on what ground that you say scandium is a transition element but zinc is not. Okay, so see, the condition for transition element is what? It should have partially filled d orbitals, right? What it should have? Partially filled d orbitals, okay, either in the ground state or in the common oxidation state. Okay, now if you see scandium electronic configuration is 3d1. Okay, argon 3d1, 4s2. Okay, now scandium in its ground state is having 1 unpaired electron, so it is a transition element. But if you talk about zinc, okay, zinc electronic configuration is 3d10, 4s2, and in its common oxidation state, that is Zn2 plus, it is also 3d10. Now you see both in the ground state and in the common oxidation state, the 3d orbitals remains 10, means they have no unpaired electrons. So that is why this one, what ground you can say scandium is a transition element because it has unpaired electron in its ground state, whereas zinc is not a transition element because it doesn't have unpaired or partially filled d orbital either in the ground state or in the common oxidation state. So chromium electronic configuration 3d5 4s1, argon 3d10 4s1. Sorry, copper is 3d10 4s1. Next, you can see scandium electronic configuration in its ground state is Ar3d1, whereas the zinc configuration in the ground state as well as in the common state are 3d10 4s2 and 3d10. Since zinc has no partially filled d orbital, whereas scandium is a transition element but zinc isn't. Third question here, name the 3D series elements having the maximum melting point. So that is your chromium, and minimum melting point is zinc. Now the reason here for zinc is it has no unpaired electron, right? If there is no unpaired electron, what will happen? There is no metallic bonding. Okay, there is no metallic bonding. Next question, why do transition element exhibits higher enthalpy of atomization? So question number 5 is also same. So you can see for both them, transition elements have stronger metallic bonding due to the participation of both N-1d and Ns electrons. Hence more energy is required to separate them and they have higher enthalpies of atomization. Next is the atomic size of iron, cobalt, nickel are nearly same. Explain with the reason. Okay. Next, if you see here, yeah, so as we move from left to right, what happens? I can say that the effective nuclear charge is increasing, right? But at the same time, the d electrons are getting filled, right? Now these d electrons create repulsion, which tends to increase the size of the atom, and the effective nuclear charge tries to decrease the size of the atom. Now these two forces are opposite to each other. But when the cobalt, iron, nickel, in that situation, in that particular configuration, the nuclear charge and the repulsion are almost equal to each other. One is trying to increase the size, the other one is trying to decrease the size, but both are equal and opposite in direction. So the net charge or the net effect will remain constant, and as a result of which the size does not change. So you can see as we move from left to right along the transition series, the nuclear charge increases, right, which tends to decrease the size. But the addition of electrons in the d subshell increases the screening effect and counterbalances the effect of the nuclear charge. Okay. Next, we'll talk about seventh question, why the density increases from titanium to copper, sorry. As you move along the period, the size is decreasing. What's the formula of density? Density is equal to mass by volume, right? So mass is increasing definitely and size is decreasing. That means volume is decreasing, and both these factors leads to increase in density. So you can write down density increases because atomic mass increases while atomic volume decreases slightly across the period, leading to a overall decrease in the density. Next, for what reason transition elements have high melting point? Again, the same reason, transition elements have a lot of unpaired electrons, and these unpaired electrons are involved in strong metallic bonding, okay, due to the involvement of d electrons. And this creates a very strong intermolecular force between the atoms, and that results in very high melting point. Next question, I think we're discussing. Okay, which element has the second highest second ionization enthalpy? Okay, and lowest enthalpy of atomization in the first transition series. Okay, second highest enthalpy of atomization. So if you see copper, okay, 1 second, and lowest enthalpy of atomization. Yes. So if you see answer here is copper, okay, because as I can say, copper electronic configuration is 3d10 4s1. Okay. Now when you remove one electron, copper plus, you will get what? 3d10. Now after that, this is a fully filled stable configuration, right? So to remove one more electron from here, it will be very difficult. So highest second ionization enthalpy is for copper. And lowest enthalpy of atomization, again here zinc, because they have no metallic bonding because of absence of unpaired electrons. Next, give reason ionization enthalpy increases along the transition elements from left to right. Ionization enthalpy. So as you see along the period, the size decreases, effective nuclear charge increases, and then that is why it is becoming difficult to remove electrons as we move along the period. So ionization enthalpy increases. So due to the increase in the nuclear charge and decrease in atomic size, the attraction between the nucleus and the electrons increases, and that is why the ionization energy increases from left to right. Next question, why manganese exhibits maximum number of oxidation state +7 only with oxides? Okay, so you can know that the highest oxidation states of an element is stabilized by oxygen, okay, as compared to fluorine. That is because oxygen can form multiple bonds. So in case of oxygen, manganese shows the highest oxidation state of +7. This is because manganese forms p pi d pi multiple bonds using the 2p orbitals of oxygen and 3d orbitals of manganese. So there is double bond formed, because of which they are more stable. Next, to what extent does electronic configuration decide the stability of oxidation states? Give example. So this question we will discuss in the next slide. Let's take 13th one now. Name the transition element which exhibits its higher oxidation state of +7 only with oxide and give reason. So same answer here, manganese is the one, and that is because it can form p pi d pi bonding with the oxygen. Next, which metal in the first series of transition element exhibits +1 oxidation state most frequently and why? So that is actually copper. We will see in the next slide. So first of all, you can check here answer number 12. Okay, to what extent the electronic configuration decides the stability of the oxidation state? So you should know that the half-filled configuration and fully filled configuration are very stable. Okay, and if the atom is in that particular electronic configuration, then that oxidation state will be more stable. So see, the electronic configurations play a crucial role in deciding the stability of the oxidation state. The presence or absence of complete or half-filled d orbitals in that oxidation state decides its stability. For example, if you see manganese has 3d5 4s2 configuration, right, and it can show +2 +3 +4 +5 +6 and +7 states, but only +2 and +7 are stable. Why? Because if you see manganese +2 will have what configuration? 3d5, which is half-filled and stable, and manganese +7 will have argon configuration, okay, due to the half-filled d orbital or completely empty d orbital. Now we'll talk about 14th question. +1 common oxidation state is shown by copper, because copper, when it loses one electron, you can see d10 configuration, which is highly stable. Now moving to 15th one, give reason copper +2 is more stable than copper plus. Okay. Now see, generally if you see, copper plus is having D10 configuration and copper 2 plus is having D9 configuration. But in the aqueous state, copper 2 plus is more stable. So what is the reason here? So copper 2 plus has higher negative hydration enthalpy than copper plus, making it more stable in water. Okay, next, why Cr2 plus is reducing and Mn3 plus is oxidizing when both have D4 configuration. So first let me explain you this one. Cr2 plus is having a configuration of D4, okay, as it is already told, and if you see Mn3 plus, okay, also has a configuration of D4. Now Cr2 plus tries to go to Cr3 plus, okay, why? Because it will get D3 configuration, and D3 configuration, as we have already studied in coordination chemistry, will be T2G3, and this is also exactly half filled. Now if you see Mn plus 3, it is in D4 configuration. It gains one electron to, sorry, from D4 it goes to D5 configuration. Okay, Mn goes to D5 configuration. Okay, now what happens when it is, because in D5 configuration it has to it will gain one electron, right? If it gain one electron, Mn2 plus, it will get D5 configuration, which is again stable because of half fill. So that is why this will lose one electron, whereas this will gain one electron. Losing one electron means undergoing oxidation. It will behave as a reducing agent, whereas Mn3 plus means gaining one electron to become Mn2 plus, gaining of electrons, so that is reduction, and it behaves as an oxidizing agent. So let's see, Cr2 plus is reducing because it easily loses one electron to form the stable Cr3 plus configuration, whereas Mn3 plus is oxidizing because it gains one electron to form Mn2 plus. Now if you see, if you compare 3d3 and 3d5, which is more stable, because one more question will be there on this basis also. You should remember 3d3 is more stable because it is T2G3. The energy level is of T2G is less than the d orbitals, right? If you remember, there are 5 d orbitals. T2G goes down and EG goes up. So this is D3 configuration, which is more stable than D5 also. So if there's a question on that also, we will discuss after some time. Now let's discuss question number 17. The E0 value of copper is positive, that is 0.34. Give reason for this. See, the E0 value depends on so many factors like your atomization enthalpy, ionization enthalpy, and hydration enthalpy. Out of this, atomization enthalpy and the ionization enthalpies are positive value, hydration enthalpy is a negative value. So copper has very high atomization and ionization enthalpy. So overall the positive value is very high, and that is why we get the overall reduction potential to be positive. So you can see here the E0 value of any metal depends on the atomization enthalpy, which is a positive value. First and second ionization enthalpy, again a positive value, and hydration enthalpy, which is a negative value. For copper, the enthalpy of hydration is relatively low compared to the high enthalpy of atomization and ionization enthalpies. This means that the energy released during hydration does not compensate for the energy required for atomization and ionization. Since the energy required to form Cu2 plus is greater than the energy released during the hydration, the overall process results in a positive electrode potential. Next, question number 18. The E0 value of Mn plus 3 to Mn plus 2 couple much more positive than that of Cr plus 3 to Cr2 plus or Fe plus 3 to Fe2 plus. Explain. Now if you see, Mn plus 3 is D4 and Mn plus 2 is D5. Okay, let's go to the next slide. Mn plus 3 is D4 and Mn plus 2 is D5, right? So from an unstable state, it is going to a stable state, right? So that means reduction will be faster, reduction will be easier, and the value will be higher. If you see, copper plus 3 is chromium plus 3 is D4 to D4. I already told you D3 is highly stable, and here Fe plus 3 is also D5 and Fe plus 2 is D6. Again, this is stable. So when you are going from stable state to unstable state, E0 value will decrease. But when you are going from unstable state, that is D4 to D5, then the E0 value will be very high. So you can see here, Mn plus 2 has a stable half-filled D5 configuration. So Mn3 plus easily gets reduced to Mn2 plus. Therefore, Mn plus 3 to plus 2 has a more positive E0 value compared to Cr plus 3 or Fe plus 3. Next, which is a stronger reducing agent, Cr2 plus or Fe2 plus, and why? So we have just discussed this one. So if you see, just a minute, let me erase this one. So if you see Cr2, stronger reducing agent, right? Reducing agent means it will reduce others and itself it will get oxidized, right? So Cr2 plus will get oxidized to Cr3 plus and Fe2 plus will get oxidized to Fe3 plus. Now this configuration is D3 and this configuration is D5, right? And this D3 is nothing but T2G3. Okay, and I have told you that T2G level always comes below the d orbital, degenerate d orbitals. We have studied in coordination chemistry. So that is why this is more stable. So that is why this conversion from Cr plus 2 to Cr plus 3 will happen more easily, or the reduction, it will be a stronger reducing agent. Okay, Cr2 plus is a stronger reducing agent first of all than Fe2 plus. In the formation of Cr2 plus to Cr3 plus, the change is from D4 to D3, okay, which is T2G3 configuration. But in the formation of Fe plus 2 or Fe plus 3, the change is D6 to D5, okay, which is exactly half filled. Since D3 has lesser energy, it is more stable, and that is why Cr2 plus is a stronger reducing agent. Next, question number 20. To what extent does the electronic configuration decide the stability? This we have already discussed. Given it to examples of amphoteric oxides, you can see Cr2O3 and B2O5. Examples of acidic oxides, Mn2O7 and CrO3. Next, the lowest oxidation state of manganese is basic, while the highest oxidation state is acidic. This is also very, I can say, common sense question. Now, if you see lowest oxidation state, okay, if the oxidation state is lower, that means it has electrons. Now it can gain electrons. Its oxidation state can increase, it can lose electrons, right? Its oxidation state will increase, it can lose electrons. Now if something is losing electrons, then it will behave as an a base, right? Base is donation of electrons. But if it is already in the higher oxidation state, it cannot further go to the higher oxidation state. Rather, it will gain electrons and come back to the lower oxidation state. Now gaining of electrons is the property of acids. So you can see the lowest oxidation state of manganese is +2. It has the tendency to lose electrons in order to increase its oxidation state, right? +2 to +3, +5, +6, +7, it can go. It can lose more electrons. Therefore, losing of electrons, manganese will be basic. In higher oxidation state of +7, there is no scope for the lose of any electrons. Rather, it will only gain electrons. And gaining of electrons is the property of acids. Clear? Next is question number 24. Calculate the magnetic moment of titanium 3+. So if you see titanium, scandium, titanium, its configuration is 3d2 and 4s2. Next, titanium 3+ will have a configuration of 3d1. So number of unpaired electrons is 1 here, and mu is equal to root over of n into n plus 2, or that is equal to root over of 1 into 1 plus 2. So that is equal to root over of 3, or 1.73 bm. Okay. Next, question number 25. Transition elements form colored compounds and give 2 reasons for that. Okay. So if you see, transition elements have unpaired electrons, and these unpaired electrons undergo dt transition, because of which we find colored compounds, right? So due to the presence of unpaired electrons and due to dt transition. Next, catalytic property. I have told you this is very, very important question. You can see how many times it is repeated. Transition metals and their compounds are known for their catalytic activity. Give 2 reasons. You should at least know 3 reasons, so that in the 3-marker question also you can answer. I've already discussed this one in the PYQs. Once more we'll talk about it. Variable oxidation. So they show catalytic activity. Okay, they show catalytic activity due to variable oxidation state, large surface area, incompletely filled d orbitals, and the formation of intermediate compounds. Next is the question. Iron 3 catalyzes the reaction between iodide and persulfate ion in the reaction. Okay, so explain the catalytic action of catalyst iron by using chemical reactions. Okay, so you can see here Fe3+. First, what it does, this reacts with this I minus and gets converted to Fe2 and converts I minus to I2, right? Now after that, what happens, this Fe2 plus, okay, which is formed here, reacts with S2O8 2 minus to give you Fe3 plus and SO4 2 minus. Clear? Okay, next we'll talk about 2 characteristics of interstitial compounds. This also we have discussed. This has been asked in 2025 as well. So they have high melting points, they have a hard retained metallic conductivity, and they are chemically inert. These 4 points are also very, very important. Next, composition of alloys brass and bronze. So brass is your copper and zinc, bronze is copper and tin. Next, question number 30. Draw the structure of dichromate ion. Okay, and what is the value of bond angle? So this is also important, you should remember. Dichromate structure is like this, and the value of bond angle is 126 degree. Here it is 2 minus is also there. Okay. Next, draw the structure of permanganate and manganate ion. So here this is there. This one is your manganate ion, that is MnO4 2 minus, and this is MnO4 minus. This is permanganate, which is purple in color, and this is green in color. Next, we'll talk about 32. What is the common oxidation state shown by lanthanoids, and mention any one consequence of lanthanoid contraction. So common oxidation state is +3, and the one consequence of that is zirconium and hafnium is almost same. Okay. Next, question number 33. What is Lanthanoid contraction and how Lanthanoid contraction influence on the covalent nature of D block elements? So now as we have understood, in Lanthanoid contraction, the size decreases, the effective nuclear charge increases. So the ability to polarize the anions increases, and as a result of which the covalent character also increases. So I'll explain it in detail. So understand here. What is Lanthanoid contraction? Refers to the steady decrease in the ionic and atomic radii of the lanthanoid elements as the atomic number increases. This is what is Lanthanoid contraction. Now what happens? Because the atomic radius of the heavier D block elements is similar to that of the lighter one, zirconium. So if you see, zirconium is there and then hafnium is there, right? And we should expect that hafnium size should be more than zirconium. But what happens? They have definitely, hafnium has more number of protons, but its size is similar to zirconium because of Lanthanoid contraction. So what happens? Despite having more protons, their size is small. Okay, so their effective nuclear charge is higher. Okay, now if you talk about what is the effective nuclear charge to size ratio, right? So here they have size is less, charge is more, so that is why they have greater effective nuclear charge, the hafnium. This increased effective nuclear charge leads to a greater attraction of electrons from the other atoms. So if suppose I have hafnium here and some other element is there, it will attract its electron very easily. Okay, enhancing the ability of these D block elements to form covalent bond. The polarization of the bonds are called as covalent bonds. So here the cations have very high effective nuclear charge, because of which they can easily polarize the anions. Therefore, Lanthanoid contraction increases the covalent character of the bonds formed by the heavier D block elements compared to that of their lighter counterparts. Okay. Next, write any two differences between lanthanoids and actinoids. So there are so many differences, any two you can remember. So atomic or ionic radii does not show much variation. Here there is much variation. They generally show +3 common oxidation state and sometimes +2 and +4. But here +3, +4, +5, +6, +7. So many oxidation states are shown. They are quite reactive. These are highly activated in the finely divided state. Electronic configuration of lanthanum is 5d1 6s2, whereas for actinum it is 6d1 and 7s2. You can write one more point here. Most of the elements are non-radioactive. Okay, they are non-radioactive, whereas the actinoid elements are highly radioactive. Okay. Next, 35. What is the composition of Mischmetal and write one use of it? So you can see Mischmetal is an alloy of lanthanum metal and iron. Here lanthanum is generally 95%. You can also mention the percentage, and iron is around 5%. And the traces of sulfur, calcium, carbon or aluminium. It is used in making bullets and lighter flint. There's one example, this one, use of it. Then 36. Separation of lanthanoids is difficult from their natural occurrence and study of actinoids is difficult. Now see, this study of actinoids is difficult can itself a 3-marker question. Okay, it has been asked in the last year model question paper. So this itself can be a 3-marker question. So I'll tell you answer like that. So even if it comes, you can easily write the answer. So first of all, why it is difficult to separate the lanthanoids? So due to lanthanoid contraction, the change in the atomic and ionic radii of these elements is very small. Hence, their chemical properties are similar. So it is difficult to separate them. Next, why actinoids are study of actinoids is difficult. Here we have 3 points. First of, they are radioactive. Their half-life values are very short and they are prepared in just in nanogram quantities. Okay. Next, we'll talk about which organic compound conversion is involved in Wacker's process and what is the formula of the catalyst. So Wacker process converts ethylene means ethine to ethanol. The main, I can say, the catalyst which is used is PDCl2 and it is also supported by CuCl2. Okay, next question, we will move to now 3-marker sections. So some of the questions are similar, but you need to write 3 points here. So let us see first of all that one. The transition elements forms a large number of complex compounds, give reason. Okay, this is for complex formation. And you can see here that is because of smaller size of transition elements, large ionic charges and the availability of vacant d orbitals. Next, give reason for the following. The spin-only magnetic moment of scandium 3+ is 0. This is very simple. Spin-only magnetic moment depends on your unpaired electrons. Since it has no unpaired electrons, so no magnetic moment. Next, alloys are readily formed by transition elements. This also we have discussed because of their similar radii and other characteristics of transition metals. The transition elements forms alloy very easily. Next, write any 3 characteristic properties of interstitial compounds. So I told you this can be a 2-marker as well as a 3-marker question. Anyway, we have discussed already 3 points here. And the 4 points we have discussed: high melting point and boiling point. They're very hard, retain metallic conductivity, and they are chemically inert. Next, calculate the magnetic moment of Fe2 plus and okay. So Fe2 plus, if you see, okay, Fe electronic configuration is argon with 3d6 and 4s2. Now Fe2 plus configuration will be what? We will have 3d6 configuration. Now in 3d6, if I draw the configuration, it is like this: 1, 2, 3, 4, 5 and 6. So the number of unpaired electrons here is 4. Now if you see root over of this one, it is root over of n into n plus 2. Okay, so that is equal to root over of 24, and that comes out to be around 4.8 bm. Okay, next write the equation for the reaction of lanthanoids with oxygen. So you have to write the equation. Okay, write down lanthanide plus oxygen gives you Ln2O3. Okay. Now, fifth question, give the reason for the following. Zn2 plus is colorless, very simple, because it has no unpaired electron. Cerium shows +4 oxidation state because it carries a noble gas configuration. Zirconium and hafnium have the similar radii, that is because of Lanthanoid contraction. So first of all, you can see Zn2 plus ion has an electronic configuration of 3d10 configuration. Since there is no partially filled d orbitals, there is no dd transition, and that is why Zn2 plus is colorless. Next one, cerium. This is important question. Please see here properly. Cerium has an electronic configuration of Xc, 4f1, 5d1 and 6s2. Okay, 4f1, 5d1 and 6s2. It can lose 4 electrons to attain the stable noble gas configuration of xenon. Therefore, it shows a +4 oxidation state. If you see +4, all these 4 electrons will be lost and it will have xenon. Next, Zr and Hf have similar radii. That is because of Lanthanoid contraction. Next, the melting point of transition elements increase up to D5 configuration. Give reason. So the melting point depends on the intermetallic bonding, and that depends on the number of unpaired electrons. So as we move from scandium towards up to, I can say, up to chromium, the number of unpaired electrons is increasing, right? D1, D2, D3. So metallic bonding also increases, and that is why melting point also increases. So you can see that as the number of unpaired electrons increases up to D5, the strength of the metallic bonding increases due to the greater overlap of the orbitals. Maximum unpaired electrons at D5 give the strongest metallic bonding, hence melting point increases up to D5 configuration. Now we'll talk about, okay, just a minute. Okay, now we'll talk about question number 6 here. What are interstitial compounds, and write any 2 characteristics. So already we have discussed characteristics, but yes, what are interstitial compounds? We will discuss now. So interstitial compounds are those compounds, see, these are in the compounds, there are certain void spaces, okay, means empty spaces. When these empty spaces are filled by smaller atoms like carbon, nitrogen, hydrogen in any ratio, there's no fixed ratio, there's no stoichiometry, they give you interstitial compounds. So you can see here, interstitial compounds are those compounds which are formed when small atoms like hydrogen, carbon or nitrogen are trapped inside the crystal lattice of the metals. Now they are usually non-stoichiometric and are neither typically ionic nor covalent. Okay, examples, so many examples are there, you can remember any 1 or 2. And characteristics we have already discussed so many times. Next, question number 7, what are interstitial compounds, and give 2 examples. So you should know, you can write down any 2 examples from here. Next is question number 8, calculate the magnetic moment of M3 plus where Z is equal to 24. So Z is equal to 24 means it is your chromium atom. So chromium has an electronic configuration of argon, 3d5 and 4s1. Now chromium 3 plus will have argon, 3d3, right? So number of unpaired electrons here is 3. So mu will be equal to root over of n into n plus 2. If I substitute here, that will be equal to 3 into 3 plus 2. So that is equal to root over of 15, and you will get almost equal to 3.7, 3.8, somewhere around this one. You can just calculate correctly, you get 3.8 something. Okay. Next, considering the elements of 3D transition series, write the element which is unable to form a monooxide. So that is scandium. Okay, scandium does not form monooxide. Having positive E0 value, that is definitely copper. A base element of Ziegler catalyst, that is your titanium. Next, name the oxometal ions for the first series of transition metals in which the metal exhibits the oxidation state equal to the group number. Okay, so there are certain metals, like if you see manganese, okay, it has a +7 oxidation state and it belongs to group 7. So that, like that, you have to give some examples. So you can see the oxometal anions of the first transition series where the metal oxidation state equals to group number are vanadate, so VO4 3 minus. If you see here, vanadate, chromate, dichromate and permanganate. Okay, vandate, chromate, dichromate and permanganate. So if you see in vandate, the oxidation state is +5 and vanadium belongs to group 5. In chromate and dichromate, the oxidation state is +6 and it belongs to group 6. In manganese, the oxidation state is +7 and it belongs to group 7. Okay. Next, in general, transition metal ions of the same charge in a given series show positive decrease in the atomic and ionic radius with the increase in atomic number. Give two reasons. Give two reasons this change in radius and name the phenomenon associated with this decrease. So we all know, in case of transition elements, what happens? The ions of the same charge, it decreases because as the new electron enters a d orbital, each time the nuclear charge increases by unity. The shielding effect of the d electron is not so effective, hence the net electrostatic interaction between the nuclear charge and the outermost electron increases and the ionic radius decreases, right? This is, and what is the phenomenon associated with this? This is called as Lanthanoid contraction. Okay, moving to the next one. One second. Yes. Question number 12. The enthalpies of atomization of zinc and copper are given. Match the correct enthalpies of atomization. So zinc has very low enthalpy of atomization and copper has slightly higher than zinc. So the reason here is because zinc has no unpaired electron. Okay, copper has at least one unpaired electron. So copper has partially filled d orbital and hence forms strong metallic bonding, whereas zinc has completely filled d orbital. So there is no metallic bonding, and that is why the enthalpy of atomization is lower here. Next question, number 14 here. Use the data among Cr2 plus and Fe2 plus, which is a stronger reducing agent in the aqueous medium. So we have already discussed this question already. Cr2 plus will be a stronger reducing agent because I can say Cr2 plus gets converted to Cr3 plus, right, which is a stable D3 configuration. Next, which is more stable in +2 oxidation state. Okay, now if you see, if it is stable in oxidation +2 oxidation state, then its reduction to plus, like M+2 to M reduction value will be very low because it is already stable. It doesn't want to come to the M state. So you can see here that this particular element has the least reduction potential. So that is why the answer here has to be Mn+2. And the reason also we know D5 configuration is there, which is a stable configuration here, right? Next, write the balanced equation for the preparation of potassium permanganate and write the structure of manganate ion. So already we have discussed preparation of permanganate is this one. This reaction we have already discussed, and the manganate structure MnO4 2-. Next, write the balanced equation for the preparation of potassium dichromate from the chromite ore. So first is iron chromate converted to sodium chromate converted to sodium dichromate converted to potassium dichromate. Next is question number 18. One second. Yeah. Question number 18. Write the balanced chemical reactions for the following. Potassium dichromate converts iodide ion in the acidic medium. So potassium dichromate converts I- to I2. So first I'll show you one basic reaction. See, Cr2O7 2-. Okay. First chromium here is in +6 state, right? It gets converted to chromium +3. Okay, now if you see this side 2 chromium, so this side it is 2 chromium. And here what happens, there is, I can say +6 to +3, there is a reduction. Reduction means gain of electron. 1 chromium +6 to +3 will require 3 electrons. There are 2 chromium, so total there will be a gain of 6 electrons, right? Then to balance this oxygen, you can add 7 water molecule. And then to balance this hydrogen, you can add this side 14H+. Okay, now this is the reaction of chromium. Now all other ions, all other reactions you have to like match with this. So for example, if I tell the first one iodide, so what is the conversion of I- gets converted to I2. Okay, 2I- gets converted to 2I2 with the loss of 2 electrons. Now how will this 2 will be equal? You have to match the number of electrons. So for that, multiply this equation with 3. So you will get here, I'll just correct here only, 6I minus 3I2 you will get, right? So I'm writing this one again. After multiplying 3, what I will get? You will get 6I minus, then you will get 6 electrons and 3I2. Okay, now you need to add these two equations to get the answer for this one. So I'll show you. You can see if I add this one, you will get Cr2O7 2-, then 6I minus, 14H plus, 6 electrons will get cancelled, 2 Cr3 plus, 3I2 and 7 water molecule. Now similarly you can write for sulfide also. Sulfide H2S gets converted to S, and then stannous SN2 plus gets converted to SN4 plus. Okay. Next, write the reaction for potassium permanganate. Okay, potassium permanganate, this important question A and B. Okay, so for iodide, see in acidic medium, I minus gets converted to I2, but in neutral medium, I minus gets converted to IO3 minus. Okay, so that we will see here. First of all, you can see manganate, MnO4 minus gets converted to Mn2 plus in acidic medium and MnO2 in the neutral medium. So I minus gets converted to I2, H plus is there, and then water is there. Next, if you see I minus gets converted to IO3 minus in neutral medium, and MnO4 minus gets converted to MnO2. Then in acidic medium, oxalate ion gets converted to carbon dioxide. Next, question number 20. How does MnO4 minus reacts with iodide ion in acidic solution and in the neutral solution? So we have already discussed, in acidic solution I minus will form I2, in neutral solution I minus will form IO3 minus. Okay, so you have to write this reaction. You can see here I minus gets converted to I2. This is for acidic medium, and I minus gets converted to, okay, just a minute. Okay, this one is slight error. This one is not there. Okay, you have to write this particular reaction. This one is for the acidic medium, okay, and this one is for the neutral medium. Okay, next we'll talk about question number 21. Among sulfuric acid and hydrochloric acid, which will be preferred for permanganate titrations, and give reason. Okay, now if you see sulfuric acid, what is the formula of sulfuric acid? H2SO4. What is the oxidation state of sulfur here? If you see, it is +6. Okay, and hydrochloric acid, chlorine is -1. Now see, sulfur is already in +6 oxidation state, the highest oxidation state possible. It cannot be oxidized further. Okay, but chlorine minus can easily be oxidized to Cl2. So if you have permanganate titration, this is a very good oxidizing agent. So if you take chloride with that, what will happen? It will get oxidized to chlorine. Okay, so that is why we cannot take chloride here, but we can take definitely sulfate, because here it is already in +6 state. It cannot be further oxidized. So sulfuric acid, because hydrochloric acid is oxidized to chlorine. Next, question number 22. Name the ore used in the preparation of potassium dichromate. So that is your chromite ore. Okay. Next, complete the following equations. So Cr2O7, 14H plus and 6Fe2 plus. So if you see this one, so as I written, Cr2O7 2 minus, okay, plus 14H plus Fe2 plus is there, right? So that Fe2 plus will get converted to Fe3 plus, okay, and you will have here 7 water and 2 Cr3 plus. Okay, just you can balance this one. 2 Cr is there, 7 oxygen, 14H plus, Fe2 plus and Fe2 plus. If you see the charge also, you can see this one is +2, this is -2, so that gets cancelled. Total net charge on this side is +14, and sorry, 1 second, 14H plus, okay, okay, we need to multiply this equation with 6 also, right? 6 Fe2 plus and 6 Fe3 plus. Why? Because there will be only loss of 1 electron, so you have to multiply 6 here. Now if you see the total charge, so this is +12 plus 14, right? 12 plus 14 will be 26. 26 minus 2 is 24. So the left side, the total charge is 24. And if you see right side, 6 3s are 18 charge and 2 3s are 6. So 18 plus 6, left side also 24, right side also 24. So the reaction is well balanced. Now if you see this one, MnO4 minus in acidic medium, right? So you have 10 I minus plus you have 2 MnO4 minus, okay, plus you have 16H plus. Now if you see, MnO4 minus gets converted to Mn2 plus, right? You will have 2 Mn because here we have 2N. Next, this I2, it will get converted to 5I2, okay, and then you will have H2O. So you will have 16, right? So 8 water molecules. So if you see now 10I, here also 10I, it is balanced. 2 manganese, 2 manganese, 8 oxygen, 8 oxygen, 16 hydrogen, 16 hydrogen. Now if you see the charge here, this side is -10, then this is -2, -12, -12 plus 16. That means +4 this side. And here also you can see +4 charge, right? So this is balanced. With the help of chemical reactions, show that chromate and dichromate ions are interconvertible in the aqueous solution depending on the pH of the solution. Write the structure of dichromate ion. Okay, so the chromates and dichromates are interconvertible depending upon the pH. If you increase the pH, means in basic solution, the dichromate ions, a color change from orange to yellow is observed as dichromate ions change to chromate ions. Okay, so chromate to dichromate, you have to decrease the pH. Dichromate to chromate, you have to increase the pH. So if I want to write the reaction here, like CrO4 2 minus, and if I write like this, Cr2O7 2 minus. Okay, so chromate to dichromate, if you are going, decrease of pH is required. Dichromate to chromate, if you are going, increase of pH is required. Next, write the structure of dichromate ion. So you can see here, so I'll clear all this so that we'll have a bit space. So you can see this is the structure of dichromate ion. Angle is 126 degree. Okay. Now coming to 24th question. So this is a slightly the same question like the question for the preparation of dichromate, but it is given in a different, slightly in a tricky way. Okay. So you see, when a chromite ore A is fused with sodium carbonate in free excess of air and the product is dissolved in water, a yellow color solution of B is obtained. Okay. After the treatment of this yellow color solution with H2SO4, compound C can be crystallized from the solution. When the compound C is treated with KCl, orange crystals of D is crystallized out. Write all the reactions involved in A to D. So if you see, first one, A is your iron chromite. Then it gives you what? It gives you a yellow solution of compound B, which is your sodium chromite. Okay. Next, after the treatment of this one, the compound C can be crystallized from the solution. So that is your sodium dichromate. And then that is treated with KCl to give you orange crystals, which is your potassium dichromate. Clear? Okay, next question number 25. A blackish brown colored solid A, when fused with alkali metal hydroxide in presence of air, produces a dark green colored compound B. Okay, this is for the prediction of manganate ions. Okay, next, on electrolytic oxidation in alkaline medium, dark purple compound C is formed. Identify A, B and C. So you can see the dark colored is the pyrolusite ore, which is your MnO2. It reacts with KOH and O2 to give you K2MnO4, which is green color, potassium manganate, and then this one is converted to KMnO4, which is purple color and solid, right? So you have found out A, B, and your C is this one. Okay, next question is to write the equation and you have to fill it. So this is again from the preparation of sodium preparation of potassium dichromate. So here first we take the iron chromite FeCr2O4. Then when MnO2 is fused with KOH and oxidized with air, you get potassium manganate, not permanganate. Okay, K2MnO4. Then when this KMnO4 at 513 Kelvin, when it is used, this is for decomposition of KMnO4, you get K2MnO4 plus O2 plus MnO2. Okay. Next, explain the preparation of potassium permanganate from MnO2 with balanced equation. Mention the gas evolved when KMnO4 is heated at 513 Kelvin. The gas evolved, this one. Okay, it is oxygen. So the reaction you have already written again, right? I'll just show you. You have already written this one 2 times. So first of all, when MnO2 is heated with KOH, you get K2MnO4. Then K2MnO4 with water gives you KMnO4. Next, what happens when KMnO4 is heated at 513 Kelvin, you get K2MnO4 plus MnO2 plus O2. So the gas that is released here is oxygen gas. Next, what is Lanthanoid contraction, and mention 2 consequences of it. So this we have already studied. The gradual decrease due to the poor shielding effect of 4f and 5f orbitals is called as your Lanthanoid contraction. And what are the consequences? Zirconium and hafnium have the similar radii and the separation of lanthanides is difficult. Basicity increases, covalent nature increases, electrode potential increases. These are points you can write down. Next, write the products when lanthanide reacts with these things. Now see, this is very simple. Lanthanoids, no, you should remember that it has a +3 charge. Okay, after that, if you solve for carbon, you should basically remember the products. It gives you Ln2C3. But with nitrogen, if you see, lanthanum is +3, nitrogen is -3. So if you do crisscross, you will get Ln. And with acids, it gives you the salts, right? So LnCl3, any, for example, HCl acid, then NaCl3 will form. Next is give reason for the following. Actinoids show higher oxidation state. That is because of the participation of 5f, 6d and 7s electrons, right? So the actinoids have the valence electrons in 5f, 6d and 7s orbitals. Since the energies of these orbitals are comparable, a large number of electrons can participate in bonding. Okay. Next, actinoid contraction is greater from element to element than lanthanoid contraction. Now, actinoid contraction is due to the shielding of 5f orbitals. Okay, and now this 5f orbitals have much more poorer shielding effect than 4f orbitals. So that is why what happens? Actinoid contraction is much more stronger here. Next question, chemical properties of actinoids are less known. That is because they are radioactive, they are short-lived, and they are produced in very small quantities. Okay, you can see B answer in detail. In actinoids, the added electrons enter the 5f orbitals, which have very poor shielding effect. As a result, the effective nuclear charge increases more rapidly, causing a greater decrease in the atomic and ionic radii. Next, among lanthanoids and actinoids, which series has more radioactive elements? Obviously, this is the actinoid series. Okay, in lanthanoids, most of them are non-radioactive. Write three consequences of lanthanoid contraction. Already we have discussed. Next, what is lanthanoid contraction and mention the cause for it. So this also we have discussed. Which gas is liberated when lanthanoid reacts with acids? Hydrogen gas is released. What is lanthanoid contraction? Write one comparison of similarity. So this we will discuss. What is lanthanoid contraction? We have already discussed. And similarity and difference, you can see both of them shows variable oxidation states, or you can say both have the +3 common oxidation state, that is the similarity. Difference is lanthanoids predominantly show +3, whereas actinoids can show from +3, +4, +5, +6 as well as +7 oxidation states. Next is to fill in this reaction with carbon. So Ln carbon at 2773 Kelvin gives you LnC2, and normal at a other temperature gives you Ln2C3, and with sulfide it gives you Ln2S3. Next, write the formula of the three different types of compounds formed when lanthanide reacts with carbon or heated with carbon. So the first one is LnC2, then is Ln2C3 and Ln3C. Okay, these are three different products formed with lanthanoids and carbon. Ln2C, Ln3C, sorry, Lnc2, Ln3C and Ln2C3. Next is give reason. Cerium is easily oxidized to cerium +4. This question we have already discussed. Cerium has an electronic configuration of xenon 4f1, 5d1 and 6s2. In +4 oxidation state, it loses all these electrons and comes to a noble gas configuration of xenon. So that is why it shows the oxidation state. Now the cerium +3 has an electronic configuration of Xc4f1. On oxidation to to cerium +4, it attains the stable noble gas type configuration, and that is why it is easily oxidized. Actinoid shows a wide range of oxidation states. We have already discussed here 5D, 5F, 6D and 7S. Okay, they have variable, they have actinoids have electrons in 5F, 6D and 7S orbitals, which are of comparable energies. Okay, hence many electrons participate in bonding, resulting in a wide range of oxidation states. Next, the second and the third transition series elements have almost similar or atomic radii. Okay, the second and third transition elements, they have similar radii. That is because of lanthanoid contraction. The atomic radii of the 5D elements get reduced, and that comes in the range of 4D elements. Okay, because of nearly equal or those of 4 elements, hence the second and third elements have the same radii. Next, name two trivalent lanthanoid ions that is colorless. There are so many: La3 plus, Lu3 plus, Ce. Okay, Ce plus 4 and Yb2 plus we cannot write because these are not trivalent. Okay, La3 plus and Lu3 plus. Next, what type of lanthanoid compounds are employed as catalyst in petroleum cracking? So generally lanthanoid oxides, okay, usually mixed rare earth oxides are used in the petroleum cracking. Next, among lanthanoid and actinoid series, which shows larger contraction from element to element, and why? That is actinoid contraction, because in actinoid, what happens, the electrons, the 5f is the one which is 5f have very poor shielding effect as compared to 4f orbital. So that is why they show much stronger actinoid contraction. So electrons are added to 5f orbitals which have very poor shielding effect. Okay, hence the effective nuclear charge increases more rapidly, causing a greater decrease in the atomic and ionic radii. Next, name the element of actinoids that does not exhibit +3 oxidation state. So thorium, you can see, okay, thorium generally has +4 oxidation state and not +3. Okay, next are some application based questions. So write the composition of the following. So UK copper, you know, it is copper 90% and Sn 4% and zinc 1%. Okay, and silver UK coins, they have silver 50% and copper 50%. Ziegler catalyst, that is made up of TiCl4 and triethyl aluminium. Name the catalyst used in the Haber's process. It is finely divided iron. Then Wacker's process, it is PdCl2 plus CuCl2, and hydrogenation of fats, nickel is used. Next, write any three uses of lanthanoids and actinoids. You can write down any three. It is used in petroleum refinery, nuclear fuel, and glass polishing, and also Mischmetal. Okay, so students, these were the most, I can say, the complete question bank and the previously asked questions from the chapter D and F block elements. So students, once again, just I want to remind you that this period of last 30 days and last 85 days for KCT are very, very crucial, your make or break period. Okay, and I, at this point of time, having confusion, having tension, having no clarity is quite common, and to help you with this, I have started this mentorship session. You can definitely join and have a one-to-one discussion with me where I can solve all your problems. The link is there in the description section, so please go and register yourself, and then we can have a one-to-one mentorship session where you will, where after this session I can guarantee you that your preparation will come on the right track. Wherever you are stuck, you will come out of that. Okay, thank you so much, and if you like this video, do not forget to hit the subscribe button, as this channel is going to be your ultimate source, ultimate, I can say, savior for KCT and PU2 2026. Thank you so much and all the best.